All right, so now we're going to look at transformations, general coordinate transformations. Okay, so think if we have some weird shaped geometry over here, right here, this isn't really a square. They're not lined up with the x-axis, right? Basically, our coordinates are curved. Okay, and we want to integrate over this region. Well, it's not really our coordinates, but our region is not a very nice shape. Okay, so I can look at a way like, well, maybe if I started with a nice square region that I want to integrate over, right? Because that's nice and easy to integrate over. What transformation do I have to do to transform this region into this blue region, right? What is this T, this transformation that when I put this region in, it spits out this weird shaped region. Okay, so this could be any sort of thing. If I can figure this out, what I'm able to do is to change coordinates into this region and integrate over a nice square, and it makes integration so much easier. Okay, so what we need to be concerned with is how does this affect our integral, right? If I integrate over this region, how does that change if I want to integrate over this region instead? So it's actually a really simple thing. All right, so here I have coordinates of u and v, and here I have coordinates of x and y. So if I have an integral, uh, triple, or it doesn't have to be triple integral, but whatever. I'm integrating over a region R, and I want to integrate a function of x and y, dx, dy, and I want to transform this into an integral over this region here. Let's just call it S, right? That's this region here. And it's going to be a function of u and v, du, dv. How does my integral change? Well, for one, right, the boundaries are obviously going to change, right? Here it's not a square, here it is a square. But also, I need to change, I need to add something. This can be determinant of the Jacobian. Okay, well, I'll explain what each of these are in just a second. But so think of it this way, why do we have to add something? So if I was to do a change of coordinates, say I would just want to integrate f of x, let's do 2x plus 5. Dx. And I want to do a change of coordinates to do a u substitution, right? So I say u equals to 2x plus 5, du equals 2 dx. So I have that du dx equals 2. Okay, so now, that's actually so, I have dx equals 1/2 du. Also, I have that, so this becomes integral of f of u times 1/2 du. Okay, so notice real quick, when I did this change, right, this thing came in, right? Where did this come from? That's exactly what this term is going to correspond to. Okay, or when I do a change of coordinates, right, and I go from a function of x and y, dx, dy, and I go to polar coordinates, right? I go to polar coordinates and I have a function of r and theta. Remember, I have to multiply by r, dr, d theta, right? So this r right here, right, that's going to correspond to this. Okay. So what is J? So J is the Jacobian matrix of the transformation. Okay, so it's going to be different for each transformation. And what it's going to be, so J for given So what is my transformation? So say I have x is a function of u and v, and y is a function of u and v. Right, so it's transforming from here to here. The Jacobian of this is going to be the matrix dx du dy, dx dv, dy du, and dy dv. Now, if we had maybe three dimensions, right, we could add more. We would add dx dw, dy dw, and dz du, dz dv, and dz dw. And we can extend this to however many dimensions we want. It always works the same. Okay, and then what I want is the determinant of this matrix, whatever this matrix is. If it's the 2 by 2 or the 3 by 3, I want the determinant of that matrix here. Actually, I want the absolute value. Okay, so the way I remember this, right, so here, notice right here, the top coordinate stays the same along the rows, right? These are all y's, these are all z's. And then here, the bottom coordinate stays the same along the columns. Okay, so the way I think of it is the ij row column component is dxi dyj. Right, so here for each, say in the first row, row 1, column whatever, right, this is going to be dx1, right, this is the first coordinate, right, x, that's x. So that's dx du, dx dv, and dx dw, and whatever else. Or if I had 2, right, that becomes a 2. Can't even see that. 2. Right, so this would actually, the second coordinate, that's going to be the y. Right, so the second row, that's going to be x2 is going to be y. So dy du, dy dv, dy dz, no, sorry, dy du, dy dv, dy dw, and whatever else. So anyways, that's how I remember it. I remember that J, the Jacobian, the ijth component of the Jacobian is dxi dyj. Or you can just remember it this way. Personally, I find it more useful to think about it this way, but it's up to you. Okay, so let's do an example. So let's do a change of coordinates here, where R is the region bounded by the ellipse, blah, and we do this transformation here. So first thing, let's go ahead and rewrite this. So I have x squared. Well, what is x? X is, actually no, before I do any of that, the first thing I do is let's compute the Jacobian of the transformation. So the Jacobian is, I'll go ahead, it's dx du, dx dv, dy du, dy dv. Okay, so we fill this in. Dx du, that's going to be 2. Dx dv, that's going to be 0. Dy du, that's 0. And this is going to be 3. Okay, so the determinant of this, right, that's this times this minus this times this. That's going to be 6. Okay, so now let's start writing our integral. So the integral, we'll figure out the regions in a second. Actually, let me put this down here. Of x squared, what is x? X is 2u squared, so that's x squared. Then I need to multiply by the absolute value of the determinant for the Jacobian. That's the 6 here. Du dv. Okay, now I need to figure out this region. So let's look at this. So 9x squared plus 4y squared equals 36. I know that x is equal to 2u plus 4 times 3v. So if we square this out, what we get is 36u squared plus 36v squared equals 36, or we just get that u squared equals plus v squared equals 1. So what this did was it took an elliptic region like this, something that looked like this, that wouldn't have been that fun to integrate over, and it converted this into a nice circle with radius 1. So now we're integrating this over a radius of 1. Yeah, we're integrating this. So this really suggests that I should do polar coordinates. So I could write this. Let me try it just without doing the polar coordinates first. So this is going to be 24, right? 4 times 6 is 24. Integral du squared du dv. So here, if we do a strip of this circle, right, we would get from negative 1 minus 1 minus what? V squared to 1 minus v squared from negative 1 to 1. And when I integrate this, I'm going to get some powers to the 3 halves, and it's just not going to be pretty. Okay, this is going to be a kind of difficult integral. So let me convert this again now to polar coordinates, and we'll see that it becomes a lot nicer. Because here we know that r goes from 0 to 1, and then we're going all the way around. So that's easy. This goes from 0 to 1 with respect to r, and from 0 to 2 pi with respect to theta. So we have 24. So we're going to have u equals r cosine theta, and v equals r sine theta. So we have r squared cosine squared theta times r dr d theta, right? This was our Jacobian of the transformation. Okay, and now I can rewrite this. This is integral 24, 0 to 2 pi, integral 0 to 1, r cubed cosine squared theta dr d theta. Now notice I have a separable function inside here, so I can break this up into 2 integrals. I have 24 integral 0 to 2 pi of cosine squared theta d theta times the integral from 0 to 1 r cubed dr. So I integrate this, I get r to the 4 over 4. The value from 0 to 1, I get 1/4, which gives me 6, 0 to 2 pi cosine squared theta d theta. Cosine squared, let's see, I'll just work this out by hand. So this gives me 0 to, no, I integrate this 0 to 2 pi, and I get 1 plus 1/2 cosine of 2 theta over 2 d theta. So I integrate, I get 6 times 1/2 theta sine of 2 theta over 4 from 0 to 2 pi theta. So we plug this in, and we have 6 times, that's going to be 2 pi, that's going to be pi. Sine of 4 pi is 0. Plug in 0 to either one, we get 0. So that's just this. I get 6 pi. Okay, next example. So we have this shape, and we want to integrate this over the ellipse, and it gives us the transformation. So a lot of times you'll be given the transformation. I expect that most of the time you'll be given the transformation, because figuring out which transformation you should use can sometimes be a bit of a pain. Okay, so let's figure out the Jacobian of the transformation. That should always be our first step. So I'll just put this here for a reminder. du, dx, dv, dy, dv. So dx du, that's going to be root 2. dy du, that's also root 2. dx dv, that's going to be minus root 2 over 3. This is going to be positive root 2 over 3. So the determinant of the Jacobian is going to be, so that's root 2 times root 2 over root 3. It's going to be 2 over root 3 minus 2 over root 3, 4 over root 3. Okay, so now I can write my integral. I'll need to figure out the bounds, but I can start with this. So I have x squared, so that's root 2u minus root 2 over 3v squared minus x, that's this, times y plus y squared. That's going to be root 2u plus root 2 over 3v squared. Okay, so this looks like a bit of a pain to expand this out, but it's going to make the integration in the end a lot easier. Okay, so here I can simplify this middle bit first. Minus root 2 over 3v, and then I'll come back to these other ones. So this is root 2u plus v squared. So this is the difference of 2 squared. So I'm going to have minus the first term squared, so it's going to be 2u squared minus, so it's minus, that's plus 2 over 3 v squared. Okay, this equals, that's going to be 4, what is it, u squared, no, sorry, not 4, 2u squared minus 2 times this, which is going to be 4 over root 3 uv plus 2 over 3 v squared. So that's this term. Plus, now I'm going to have the same thing except with all positives. So I have 2u squared plus 4 over root 3 uv plus 2 over 3 v squared minus 2u squared plus 2 thirds v squared. Okay, so the whole point of this is we have a lot of stuff cancel out. This cancels out with this, and this cancels out with this. So now we have, let's see, so 2u squared. So we have 2 over 3 v squared plus 2 over 3 v squared plus 2 over 3 v squared. That's 3 times 2 over 3 v squared, which just gives us 2 v squared du dv. So finally I get 2 integral u squared plus v squared du dv. So this looks like it might at the end give me like polar coordinates to work with, especially since I'm working with an ellipse. But let's go ahead and see what does this region correspond to. Okay, so here notice this thing, it's exactly the same as what I have inside the integral. So I can actually copy all of this work that I did expanding. So here, this big thing, it's going to simplify, or this thing, it's going to simplify minus xy plus y squared equals 2, right? So this is exactly what I had in here. So all the same work holds, and it's just going to simplify down to this, right? So it's going to give me 2u squared plus 2v squared, right? That's what this simplified to, equals 2. And I have u squared plus v squared equals 1. Okay, so if this is u and this is v, again, I have this nice circular region to integrate over. And I could, do it like this and integrate, these from negative square root of 1 minus v squared. But that's really going to give me some ugly integrals to do here. Okay, so instead what I'm going to do is I'm going to integrate this with respect to r from 0 to 1, and then with respect to theta from 0 to 2 pi, and do a change of coordinates. So here, again, I'm going to have u equals r cosine theta, v equals r sine theta, which means that I will have the integral from r equals 0 to 1, and then from theta, going from 0 to 2 pi, of r squared times r dr d theta times 2. Okay, so this is separable, so I have 2 integral 0 to 1 r cubed dr, integral from 0 to 2 pi d theta. So this integrate, I get r to the 4th over 4 from 0 to 1 gives me 1/4. And then here integrate, I get theta from 0 to 2 pi, that just gives me 2 pi. So cancel, 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 and I just get pi. That's my answer. All right, so you're not always going to have to convert to polar coordinates at the end. Sometimes, this integral that you get at the end will be nice and simple to integrate. But it's just an example of how, sometimes we can do multiple transformations to get something in the end that's actually saves us a lot of work, right? We can actually integrate this fairly easily. Whereas up here, that's integrating this over this domain in x and y coordinates would be really nasty, right? Because we'd have to write this as a function of like y equals 2 minus something, and that would not be pretty to look at. All right, hope that helps. See you guys later.